Jessica Yanes. Jessica is a PhD from the 37 cycle. She's enrolled in the Environmental and Infrastructure Engineering program. And she's working under the supervision of Professor Antonelli in the Safe Water Research Group. Her research tackles the fate and transport of micropollutants in urban water. And specifically, she is working on the development of new strategies to monitor and to assess the environmental risk that is associated with this kind of contaminants. So without further ado, from my side, I just leave the floor to Jessica.
Thank you, Chiara. Good evening, everybody. Today we talk about my PhD project that focuses on managing pollutants and micropollutants contamination in integrated urban wastewater system, focusing on risk assessment and mitigation strategies. But what is an integrated urban wastewater system? So with this term, we mean these infrastructures of the sewer system, the sewer overflows in the sewer system, the wastewater treatment plant, and the receiving water body that receives all the discharges. The system in the urban area is usually combined, a combined sewer system, which means that during dry weather, we have the collection of the wastewater into the sewer system, and we have the discharge in the river only of the effluent of the wastewater treatment plant. While during wet weather, the same sewer system collects also the stormwater. So this is very clear that when there are rain events, the capacity of the system cannot collect all the stormwater inside the system. So there are these structures here that allows the water to overflow and go out the sewer system directly to the receiving water body without any treatment. And the remaining part of the sewer can go to the treatment plant. So during wet weather, when we have rain events, we have the discharges of CSOs, that are these combined sewer overflows, that are many along the sewer system. And then we have the bypass, that is a kind of a CSO, but is right before the wastewater treatment plant. And then, of course, we have the effluent of the treatment plant, but this effluent is treated while the other discharges are not treated. So the differences are that during dry weather, we have only this discharge, that is a continuous discharge of water and is a treated flow. While during wet weather, we also have CSOs and bypass that are intermittent, which means that they activate and they discharge only during a specific time, usually during rain events, during heavy rain events, and they are untreated. They can discharge not only conventional pollutants, but also micropollutants. What we mean with micropollutants? So there are many anthropic sources in urban areas, and they release different types of micropollutants, and they are not removed in the wastewater treatment plant. This means that in the environment we can find them at trace concentrations. We mean nanograms per liter or micrograms per liter. And with this concentration, even though they are very low, they can be potentially hazardous for human health and the environment. While with conventional pollutants, we mean the typical pollutants that we find in the wastewater treatment plant that are associated with the wastewater flow. They are well removed in these plants, and we refer usually to solids, organic matter, nutrients, and pathogens. Oh, sorry. Moreover, we can say that this system that I just described to you can be defined as a gray system, which means that typically we have pipes. The infrastructure is made out of pipes that collects all the sewer system. But actually, with these kind of new regulations related to, for example, the Green Deal or the green energy, there is actually a kind of shift towards green cities, also called water-wise cities, where we have more natural areas inside the city, so we have less gray and more green. And we also have green energies that can use water, and water can also be reused inside the urban area, also for agricultural purposes. So this is actually the current shift for cities, but what about water pollution that comes from these new practices? So in this context, my PhD tries to provide tools for safe management of water pollution in urban areas. Specifically, we try to identify the critical sources and the critical compounds that can be present in the cities. And we also want to assess the effect of climate change on the pollution. And for the pollution that we find, we want to treat the contaminants and remove them. So we need to know which mitigation strategies to realize and how, and also where, on which of these discharges. And last but not least, we want to assess the environmental risk in the receiving water body. So this is the goal. And to do so, we developed 5 different tasks. The first 3 are related to the pollution discharged during wet weather, and the last 2 are related to the pollution discharged during dry weather. So starting from the first one, we started with a literature survey, and we wanted to assess the environmental risk using the data that are actually currently available in the literature, and perform a risk assessment with these data that are available, that we know. And then, after this work on the literature, we performed several monitoring campaigns on a case study where we monitored the bypass of a treatment plant during dry weather, and during wet weather, sorry. And we also monitored the dry weather in order to do some comparisons of dry and wet weather, and we also looked at different events and different times during the same event to also look at the dynamics. In the end, on the same case study, we realized a model of the entire sewer system and bypass, CSOs, and wastewater treatment plant in order to assess what is the overall risk caused by an integrated system. Moving to the dry weather pollution, we started with the assessment of the environmental risk caused by this water-wide city approach to understand whether this approach that seems to be innovative is also good for the water pollution, or there are some risks that need to be addressed. And then we focused on the quaternary treatments that are treatments that needs to be implemented in the wastewater treatment plants in order to remove micropollutants. But right now, we still don't know what are the best combinations of these treatments, so we need to further investigate this. This is the, let's say, status of each task, and all these tasks were developed with the DHI, that is a software company for water, and DTU, the University of Denmark, where I spent 6 months during last year. Starting from the first task, so the literature survey risk assessment based on the literature, we wanted to understand from this data which discharges and pollutants cause the highest environmental risk. So this is the system that I just described to you. We have the sewer system with the CSOs that are many, and then we have the bypass and the treatment plant with the effluent. And we wanted to know for each of them the concentrations that they discharge and the volume that they discharge. And also we wanted to know the flow rate of the river in order to calculate the risk and also take into consideration the dilution factor. We did this collection of data on several cases, but what we first found is that there are a lot of studies on the effluents, but very less on the wet weather discharges. And also on the bypass, we really have very few references. And moreover, if we look at these studies, they only focus on one or maybe two or few discharges, and they don't compare the different types of discharges that actually impact on the same river. So for this reason, we realized an archetype system that was defined with probabilistic distributions for all the parameters that we included in our study for the risk assessment. So the concentrations, the volumes, and the flow rate of the river were all described by probabilistic distributions in order to have, in the end, a kind of idea of the risk of the whole system, not only of a single discharge. So we performed the risk assessment, a chronic risk assessment, because it was performed on a 1-year time scale. And we divided the two procedures for micropollutants and conventional pollutants because they have a kind of different impact. For micropollutants, we have a chemical risk that we can measure, comparing it with a toxic level that is known. And we put inside the risk calculation all these probabilistic distributions that in the end gave us a risk curve, a probabilistic risk distribution of the risk. Then for the conventional parameters, we used an ecological status index that can tell us the quality of the river with these, let's say, indicators based on the concentrations of the pollutants that we have in the river. So this is just an overview of the method. But what we obtain actually is distribution of the risk for each discharge and for each parameter. We have here the chrysin for micropollutants and diclofenac. And for the conventional parameters, we have E. coli and ammonia. And here, for the risk, you have the red line that indicates above we have risk, and below we don't have the risk. We have not high risk. And here, for the conventional parameters, we have these lines that indicates the quality of the river. So above the red one is very, very bad quality. And here we have intermediate situations. You can see that based on the pollutants that we look at, the main responsible can be either the wet weather discharges, such here for chrysin, or can be the effluent, like for diclofenac. So we saw, looking at different other compounds, that for pharmaceutical, the main responsible is the effluent, while for other micropollutants like hydrocarbons, heavy metals, and here should be pesticides, we have more impact from wet weather discharges. And for conventional pollutants, E. coli is the main responsible of the bad quality in rivers, while the effluents are responsible for phosphorus and nitrates. Moreover, we wanted to assess also the climate change impact, and we did this changing the flow rate of the receiving water body and the volumes discharged by the different sources. So changing this factor, we realized 3 different scenarios: the worst, medium, and safe in the formula. And we also wanted to assess the risk assessment procedures present in literature, because they don't have a standardized procedure. They use different percentiles of concentration or percentiles of risk quotient. So we wanted to understand, if we do different combinations, what is the main important parameter that affects the final risk. So just to give you an idea, we did all these combinations, and here are the results summarized. But what we found is that the risk is actually more sensitive to the change in the possible dilution rather than to the change in the possible concentration. So if we want to do a risk assessment, we first have to define a range for hydraulics, at least a range. And we saw that when we define this range, it doesn't need to be very specific, then concentration is the parameter that affects actually the risk. But due to the large variability of the concentrations that we have during wet weather, high difference in risk can be observed if we change the percentiles of the risk quotient, because we have a very skewed distribution. So if we look at the median or at the 90th percentile, we have different values, very, very different values of risk. This work is published, and if you want to know more, this is the paper. And moving to the second task, we focused on the bypass because we found that in literature there are very, very few studies. And so we wanted to understand what we found in the bypass, and also we wanted to search more contaminants with what we found in literature that are very, very different among the literature studies. So we wanted to include all the type of pollutants that we found in order to have a kind of overall idea of the risk. So we selected a case study in northern Italy, and we looked, as I said, at the treatment plant, at the bypass, and we also looked at the effluent both in dry weather and in wet weather, and we also sampled the influent in dry weather. We performed 7 wet weather campaigns and 4 dry weather campaigns, and we monitored all these pollutants. So, if we look at the just at what was found above the limit of quantification, not at the concentration, but only at the frequency of detection, here you can find in blue the frequency of detection in wet weather in the bypass, and here the frequency of detection in dry weather. And the other red one are not detected compounds. So you see that in the bypass we have more metals detected and also more pesticides, and some PFAS are also detected in the bypass. So this is just a first screening of the monitoring. Then we wanted to compare the concentrations found in wet weather with the concentrations found in dry weather. So we calculated the ratio between concentration in wet weather and concentrations in dry weather. And this is what we found. So we have the highest concentrations in the bypass here and the lowest here. And if we see the highest concentrations, in gray you have the metals mainly that have this kind of behavior together with some like solids and the pesticide and COD. So we can say that we see a kind of behavior based on different groups that are found in the water, and we try to realize a kind of correlation analysis since we found this kind of different behavior. And we saw that we have significantly higher concentrations of metals, but there is a presence of correlation between different groups of contaminants. And we found here the biggest group is the metals with the solids. But this work is currently, let's say, under construction. So I will talk about some few more analyses that we've done. We wanted to understand also if the type of rain event has an impact on the concentrations that are found. And we saw that if we clusterize the data set based only on some very easy parameters that are the conductivity and the solids, we see that there is a cluster with high concentrations that is all the data collected during small events. So when we have a very, let's say, small light rain events, we actually have high concentrations in the bypass. While when we have medium, large events, we found that we have a first cluster for the beginning of the bypass, where we have higher concentrations, and the second cluster for the end of the bypass, where we have the lowest concentration. And if we compare the three clusters, we see that they are kind of decreasing for the conventional pollutants and the metals, while for micropollutants, the behavior is different. So we still need to understand better why. And we thought this could be for the first splash effect that we saw is different based on the contaminant. And also we want to investigate the sampling frequency, because we did the sample campaign with different frequency, and so we want to understand if there is a kind of impact on the risk assessment, on the final risk that we found. Yeah. Moving to the last task of the wet weather discharges, we wanted to model this system where we perform the monitoring campaigns. And so we wanted to understand if we can predict the impact of the CSOs that are those discharges that are not currently monitored by the water management. And we want to understand also if we can assess the impact of possible future mitigation strategies in order to give an indication on what can be done to mitigate the risk. So we realized the hydraulic model for the system and the water quality model. That is also what is required by the revision of the Urban Wastewater Treatment Directive. And this is the system where we have this part of the plant that was monitored in task 2. And with these results from this task, we can calibrate all the contaminants released by the sewer system. So after a long part of data collection and the system conceptualization, we define a system in West, which is the software from the partner company. And here we have the system, the sewer system, where we included 28 catchments and 26 CSOs. And we use data from 8 rain gauges. While for the treatment plant, we used the water line, and we kind of simplified the treatment plant because we didn't need all this large part. So after the definition of the system, we moved to the calibration. And we did the calibration both in dry weather and wet weather. And we calibrated the hydraulics and the water quality. So what we had was just the flow rate at specific points of the sewer system, and at the influent and the effluent of the treatment plant. So for the flow rate, we were kind of safe. But for the CSOs, that were actually what we needed to assess the risk, we didn't know the volumes discharged by the sewer system, but we only knew when they were discharging, so when they were activated and when they were deactivated. So we needed to calibrate the system only on these activation times. While for the bypass, we knew the volume discharged. For the water quality, we calibrated the conventional pollutants, and we are now with the monitoring campaigns calibrating the micropollutants also in dry weather, wet weather, at the influent and the effluent of the treatment plant. Just a few results for the CSOs. Here you can see the activation time, the measured time, and the predicted time. The closer to this line, the better the calibration. And here you have the deactivation. And here we can see that we can compare our result with the reality, and the calibration was quite successful. While for the volumes, we didn't know if actually the CSO's volumes were correctly predicted, but we could say something on the bypass. Here, this is what we measured and what we predicted, and the relative error is lower than 6%. What we wanted also to highlight is that the CSOs discharge almost 35,000 cubic meter. That is way much higher than the bypass, that is almost 20,000 cubic meters. And this was during medium-sized event. So the CSOs are discharging more than the bypass. While if we look at small-size event, we see that the main contribution comes from the bypass. So this is kind of, I think, important to understand, because if we need also to assess the mitigation strategies and understand where to localize them, we need to understand that depending on the event, we have different, let's say, risks depending on the locations. So, moving to the water quality, for the conventional pollutants, I will show you just the calibration in dry weather. And here you can see that with the blue box plot, we have the measured concentration from 70 days. We have 70 days to calibrate the data. And the orange dot here is what we predicted with our model. And we were quite happy with this result, because actually, usually when you have a treatment plant, you put your input data in the software, while we were able to generate the data with our sewer system. So we model the sewer system and we know what we enters the treatment plant. And this is not usually done. And then in the effluent, we had a lot of measurements below the LOQ, so we tried to reconstruct the data. But with our calibration, we only wanted to be able to say if the data was above or below the LOQ. So also here, we succeed in our objective. So the next steps, we still have some work to do here, and we need to calibrate the conventional pollutants in wet weather and the micropollutants, but in dry weather and wet weather, using the analysis that we performed in task 2. Then we want to evaluate the annual loads released from each discharge to perform the risk assessment. And moreover, for the mitigation strategies, we want to compare two different technologies that actually are the first flush tanks and natural-based solutions. And in the end, we would like also to assess the effect of climate change on the environmental risk. Changing maybe the dilution factor, something will happen. Moving to the dry weather discharges, we first started on the water-wide city approach, looking at the micropollutants released by these systems. And we actually chose a case study. So the case study is currently in Milan, and is a project that has been discussed for a long time, that is the reopening of the Navigli, which means the project wants to reconnect the upstream part of the canals with the downstream part of the Vettabbia canal, where there is a wastewater treatment plant that serves a large area and is actually reused for irrigation currently. And also, not only the hydraulic reconnection, but some green practices are foreseen, such as the groundwater pumps, because we have in Milan the problem of the increasing of the groundwater level, and we need to lower the level to maintain the underground infrastructure, like the metro. And moreover, with these pumps, we can use the water to generate clean energy. So there are some projects to use the water in this way, and we included this in our system. Then we wanted also to assess the impact of the separation of the sewer system that allows a better performance of the treatment plant and not discharging the untreated wastewater. Moreover, we also included in the system the reuse of the wastewater for irrigation that allows the reduction of freshwater use and the availability of nutrients that are already in the water. So we can use the water that is already a good water for agriculture. This part is currently already present in Milan. So what we needed to implement as a future project is all the part with the groundwater heat pumps and the separated sewer system. We did this project again in the software West, and as I said, we looked at these 4 water management scenarios, and also we looked at different climate change scenarios, and we wanted to compare different, let's say, scenarios where we suppose that there is an increasing of rain or we have a long drought. So we wanted to see all the different possibilities. The micropollutants that we chose are PFOA, PFOS, and pyrene. We chose those micropollutants because they are those found in all the sources that we included in our system. And with this work, we performed different analyses. At the beginning, we checked the prediction of the model in the baseline situation, and we look at the concentrations in different points of the system, of the canals. And for the risk assessment, we calculated the chronic and the acute risk that derives from the European regulation and the environmental quality standards. Not only we wanted to see what is the value of the risk, but also we wanted to see how many hours is the risk above the threshold. And how much is above is just a little bit, so we can just use a small mitigation strategy, or we need a very big treatment. And in the end, also, we focused on the fraction where we found the micropollutants. So is in the dissolved part of the canal, or is attached on the solids. These are the analyses, and I will just show you the concentrations. Here we have the locations that we looked at in the system. So the inlet after the pumps, after the sewer system, and after the wastewater treatment plant. And in the end, at the outlet, so where the canal finishes. I didn't mention, but the groundwater heat pumps, they withdraw the water from the groundwater, but they discharge it into surface water. So this is currently already done, and it's discharging into the sewer system. So why not discharging to the canal if we have clean water? So these are the scenarios and the concentrations of PFOA and PFOS in the different locations. We see with different colors the different scenarios. And we first see very clear that these orange here are the highest concentrations, and they are caused by the release of PFAS coming from the shallow groundwater. But what about these concentrations? Are they actually a risk or not? So we look at the acute risk. So we see that actually there is no acute risk for PFAS. And for the chronic risk, this really depends on the legislation, because actually there is not a large research on this. So the legislation reflects the lack of knowledge on different levels of toxic levels, let's say, of the target for the legislation. So if we look at one legislation, there is a risk, there is an exceedance of the threshold. If we look at another legislation, there is no exceedance. Then if we look at pyrene, here we see clearly that the higher concentrations are present after the discharge of the separated sewer system. So the main contribution comes from the stormwater. So here, for the risk, we saw that actually these concentrations are a risk for the environment, both for the acute risk and for the chronic risk. So we focused on this contaminant to evaluate the scenarios of climate change. Summarize some main results. as I said, we look at the baseline situation to check the model prediction, and we found that we can predict correctly the fate of pollutants. And there is no acute risk for PFAS, but pyrene can cause acute and chronic risks along the waterway due to separated sewer systems. But this risk can increase also due to climate change, with the highest pollutive fraction, that is the particulate one. So if we want to implement some mitigation strategies, we can think about something that separates the solids part with the dissolved part. This work was submitted and accepted, so hopefully we will soon publish it. And moving to the last task, this is coming soon because we just have the, let's say, the concept of the work. And here we want to understand in the context of the new directive, we know that the wastewater treatment plants needs to implement quaternary treatments, but we don't know what is the best treatment or how we should combine treatments for a correct removal and also a cost-effective removal. So our idea is that here we have micropollutants entering the wastewater treatment plant. We have activated sludge system for the removal of organic matter, and then we should put something here. These are the possible configurations, but we don't know actually which one is the best. So we realized a model for ozonation, and we are working on models for absorption, both as a powder activated carbon and a granular activated carbon. And then we want to set a fixed removal, the 80% removal that is required from the directive. So with this set removal, we will look at the different combinations and see the costs, the OPEX and the CAPEX costs. And with this output, we can say if actually we should implement one configuration or another one. This was all for this work. And then in the end, we can say that for the wet weather discharges, we saw from the literature that we can realize a stochastic procedure for risk assessment, but there are gaps for the bypass and for the overall integrated urban wastewater systems. Then we performed a monitoring campaign on the bypass influent and effluent with a large spectra of micropollutants and conventional pollutants. Then, in this system, we realized a model for the prediction of the pollution released by the whole system. And moving into the dry weather, we assessed the environmental risk of the water-wise city approach for granting a safe transition. And we are developing techno-economic analysis for the quaternary treatments to allow safe and cost-effective removal of micropollutants from wastewater. So that was all. Thank you for your attention and for listening and coming.